the short-time Fourier transform. Yet another transform. In contrast to some of the other transforms you've learned in your undergraduate degree, this one is actually useful and also very cool. I'll start with a question. A guitar chord. One chord that gets played on a guitar. I'll play a snippet of that chord. A very short snippet. We can take the spectrum of that snippet. Okay? And before I've shown you that you can actually figure out whether this is a G major chord or a C major or whatever by looking at the frequencies at which that happens. Question 1. Does the guitar chord contain more than one frequency? Yes, it's on the spectrum there. We know it contains more than one frequency. Question 2, is it a stationary signal? Okay, before that, someone tell me what is a stationary signal? A stationary signal is a signal that intuitively doesn't change its characteristics over time. Okay? A stationary signal, if I looked at it from now until 10 minutes from now, and I looked at it from 30 minutes to 40 minutes from now, the content, the spectral content of that signal shouldn't change. It's a little bit more complicated than that. It's actually because it goes into probabilistic theory, blah, blah, blah. Okay? But formally, it means that basically the probability distribution of my signal doesn't change from now into 20 minutes into the future. That's formally what it means. Yeah, can you give me an example of a non-stationary signal? Quickly say a sentence. Just say anything. Sing a song. You said no. The signal no is a non-stationary signal. You said no. That little wave that came out of your mouth is a non-stationary signal. Because if I look at the start of what you said, that is different from oh. And so you produced a non-stationary signal. Most stationary signals it doesn't exist. It's just like rubbish, right? It's just something that's in math land. Okay, so a guitar chord, is that stationary or not stationary? Okay, I'm not sure. A guitar chord that goes on forever and ever and ever and ever and ever in the same way, that is a stationary signal. Okay, so we can think when the guitar chord here plays, you can kind of think of that as a stationary signal. But now there should be no confusion. If I play this one, this thing, is that a stationary signal? No, it's not, because its spectral content changed over time. Okay, is everyone with me? Okay, awesome. Okay, so what we're going to do today is look at the short-time Fourier transform, which helps you to deal with non-stationary signals. In other words, stuff in the real world, not rubbish that we make up with mathematics on a piece of paper to test you with. Things will get a little bit mathy for a little bit, and then I'll come out and actually show you examples of the short-time Fourier transform. It gets mathy because here I took one of the purest forms of non-stationary signals. Someone explain to me in words what that is. Okay, I'll start. It's a sine wave. Yes? It's been frequency modulated. That's not plain words. Those are fancy words. But it's true. So it's a sine wave that over time, its frequency changes. Okay? And that is a non-stationary signal. Over time, its frequency changes. If I look in a window here, the frequency content in that little window is different from the frequency content in that window. Okay, so the first thing we're going to do, and we're going to be a little bit formal, is derive what the frequency of this thing is. I'll just remind you of something from your continuous signal processing course. So if you have a sine wave looks like this, and then there's some stuff in the brackets there, and I ask you, what is the instantaneous frequency of this thing? In other words, I ask you, what is this frequency at 500 milliseconds? So you say, take the derivative of the stuff in parentheses there, which is theta t. Okay, that actually gives you angular frequency. I want normal frequency in hertz, so I just divide by 1 over 2 pi. And this is the equation for instantaneous frequency at a specific point in time. So if I have this signal and I've expressed it mathematically, then if I do this, this thing will tell me what is the frequency of this thing at 200 milliseconds or at 500 milliseconds or whatever value of t I stick into this equation here. Everyone happy? Sufficient. The dumbest example of this, and this is the one we've used so far in the course, okay, what is the instantaneous frequency of this thing? F0, and it stays F0 forever and ever. You can see it because for this case, let's just go through the steps, and then the derivative of the stuff that's in like parentheses here, so this stuff, we take that derivative. Grade 1, you learned that the derivative of this thing is just, it's in terms of t, so what's the derivative there? 2 pi f0, 2 pi f0, and then 2 pi and 2 pi cancel out, and so this thing's instantaneous frequency is f0. If I look at 500 milliseconds, what's the instantaneous frequency? f0. If I look in an hour and a half from now, what's the instantaneous frequency? f0. That is a stationary signal. Let me actually give you the equation for what happened here. And so what I did to produce this thing is I took the following signal and then I sampled it because I had to plot it on a computer, but this is the continuous sinusoid that I used. Okay, this is a little bit crazy, but this thing now in here, that's my theta t inside here. Okay, now why did I pick this weird form? Because I get an interesting instantaneous frequency when I do this. So instantaneous frequency, I get it by doing 1 over 2 pi d dt of theta t, which is just that thing there. Okay, I'll plug it in. What is the derivative of this monstrosity in terms of time? The first term, it's just 2 pi f1. Okay, the t disappears. Then the second term is plus sine. Cosine changes into a plus sign. Sorry, cosine changes into a minus sign, but we have a minus there, so that becomes plus sign. f2 over f3 sine, and then we keep everything in the brackets there, 2 pi f3t. And then it's the chain rule of differentiation, so we also need to take the derivative of the inside thing with respect to t, so we get 2 pi f3 there. Okay, and then a ton of stuff cancels out here. This 2 pi cancels out with that one and that one. This f3 cancels out with that f3. And we end up with a little equation here, f1 plus f2 sine 2 pi f3t. Okay, now tell me about the instantaneous frequency of the signal. It's non-stationary, so it's a function of time. Tell me what happens over time. What happens at time point 0? What's my instantaneous frequency? F1. And then as I move on at time, what will happen to my instantaneous frequency? It will change to what? Yeah, so that's exactly right. So at time step 0, so you can actually plot a little plot now. Just pay attention to what we're plotting here. We'll plot the instantaneous frequency over time. So this is the frequency. So the sinusoid is going tung, 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 tung. How fast is it going up and down? Okay. So at time step 0, and we'll think about this over time. So at time step 0, what's the instantaneous frequency? F1. Okay. And then what's going to happen is over time, I'm going to go faster and faster, and then I'm going to go down, and then I'm going to go faster and faster, and then I'm going to go down, okay, and this goes on and on. And actually, it happened in the history as well. This is F1. This is the frequency there. What is this point here? What's the amplitude there? F1 plus F2, thank you. F1 plus F2. And the point here is F1 minus F2. So, okay, and the point here, this is, yeah, what is this point here in terms of time? 1 over F3, thank you. Okay, that's exactly right. And so what will happen is at 1 over F3, I'm back at F1. So, concrete example, let's just do a concrete example. Let's say F1 is 8 kilohertz and F2 is 5 kilohertz, so this gives me the height here is 13 kilohertz, and that means that the bottom one here is 3 kilohertz. Okay, so what we have is we've got a sine wave that as we move over time changes frequency, which is exactly this picture here. So we start out at I don't know, I think at 80 kilohertz, and then it goes faster and faster to 13 kilohertz, and then it goes down to 3 kilohertz, and then it goes faster to 8 kilohertz, and then it gets down to 3 kilohertz. Okay? And what I've plotted here is a sampled version of that signal. Pretty weird, non-stationary signal, but if we can figure out what to do for this signal, then we've solved a lot of our troubles in life, basically. I took the continuous signal, which is this one here, and then I sampled it with a sample frequency of 44.1 kilohertz. Okay? So I get a bunch of samples. I took a really long window, okay, on the computer. Took a really long window of that sampled thing. It's sampled, it's in NumPy, so I can do something with it. What do I do to get its spectrum? What's the one Python command that you know? FFT.FFT, which gives you the DFT. So I generated this whole thing, and then I took the FFT. Now, just remind yourself of what's happening. It's like a sine wave, but that impulse is going like this, right, in the frequency domain. The impulse is really going from 3 kilohertz to 13 kilohertz, and then kind of going back, and because it's a non-stationary signal. It's not the proper way to think about it, but it is a way to think about it. What happened when I took the DFT? What does the DFT look like? I wouldn't be able to answer that question without having done it, so I just did it. It looks like the Eye of Sauron, right? The little eye there. Okay, cool. Well, wonderful. Good for you. We can see some stuff on this plot. I think this is 3, and I think is that 13? So what does that show you? This is the DFT, our wonderful friend. If you look at this picture, just this picture of the DFT, can you tell me what happens at 10 milliseconds or at 30 milliseconds or 10 minutes from now? Can you tell me the instantaneous frequency at any one of those points? No, you can't. You could, when you looked at this thing, I can ask you, like, what's the instantaneous frequency there? And you can guess, oh, it's higher than what's here. But then when I do the DFT, actually all that information got lost. Okay, and I can't see anything. Okay, that makes me sad on the inside. Okay, so this is what the short-time Fourier transform will help us with. Quickly, how would you fix this? I want the DFT, but I want one that can tell me what's happening right now. Okay, and I want one that later on tells me what happens in 10 minutes from now. Forget about sine waves for a second. With one chord, I could see basically the values of the pitches at different points. But the moment I take 2 chords, okay, then I get this thing. And this thing is like a combination of both chords. So this is a combination of but just looking at the DFT picture that I have at the bottom here, I can't tell you which chord is happening when. Okay? And the STFT will allow us to do this. Okay, so this is actually the short-time Fourier transform. This is just what we'll do. We'll have a signal, and this is an actual real signal. It's a little speech wave. And what we'll do is we'll take a little window called a frame, and we'll take the DFT of that frame. Boom. Then we'll move this window on to a next point in time, and we'll take that little frame. Okay? And then we'll move it on to a next point in time and get another frame, and so on. Okay, everyone happy? Yes. Okay, so the question is, why are there gaps between the frames? Actually, in real life, when you take the STFT, you make sure that there isn't gaps. The reason that there's gaps is it makes it easier to draw. Okay? But in real life, you make sure that there's 0 gaps. Actually, that was a lie. In real life, I make sure that there's a bit of overlap between the windows. Okay, so I'll take this window here, which is n samples, and then I'll have a little window here. Okay, so n is the window length, that's the technical term, and r is basically the hop length. It's how many samples do I take between windows, okay? And in the picture here, there's gaps. I don't want gaps. So in real life, normally, there's overlap between the two. What can you tell me about N and R in real life? Which one is bigger? N is bigger. Okay, so in real life, you normally have overlap. R is smaller than N. Okay, the frame rate, this is something that's important. You need to know how many frames are you getting out of this thing a second. Let's just think about this. So the time between frames, time, like actual time in seconds between frames, that's equal to R times my sampling period. Okay, that's just how much time there is. R is in samples. So this just tells me like seconds per frame. That's the unit of that thing. How many seconds do I take for one frame? So then if I flip this and I have 1 over RT, then that tells me how many frames do I have per second. Decision. How big do we make our windows? How big do we make N? Who wants, like, just this window here? Forget about R for a second. Just the window here. How long do we make N? Who wants a large N? You've got two choices, a large N or a small N. I like that reason, okay? Yeah, so if you take a very long window, you get less side lobes. I like that, okay? Also, if I take a very long window, remember it's a DFT. So with a very long window, if I take a window of 10, then I'm going to get 10 samples in the spectral domain. If I take a window of 10,000, then I'll actually get, with the DFT, I'll get 10,000 points in the spectral domain. So I really like what you said. Okay, the rest of you, why did you not vote for long window? Someone fight these guys. We've got infinitely long windows now. Why would we not want infinitely long windows? If I take an infinitely long window here, then the spectral characteristics, I'm basically going to capture the spectral characteristics of that whole thing. Which then I'm back in this land where I can't distinguish my chords. Because I just said, well, take a long window, and now I don't actually have good time resolution. So the right answer is, I don't know, okay? But it's not infinitely long windows, and it's not super short windows either. There's a trade-off, and it's a broken world, so you can't get best of both, okay? You need to make a decision. And so basically the right thing is you take a window that's as long as possible in order for the signal to still be stationary in there, okay? Because that gives me good spectral resolution. But it still needs to be short enough so that the signal is stationary within that window. Is everyone happy? The short time Fourier transform, you take these windows, tunk, 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 they're normally overlapping. But what I want is I actually want to visualize all of those the DFTs. I want to visualize all of those DFTs in just one go. And that's what this visualization thing called the spectrogram actually allows us to do. So how the spectrogram works is, on one axis, you've got time. And then on this axis, we have frequency. And on this axis, we basically have the DFT magnitude. So if I took a slice, let's say I took a slice here at 100 milliseconds, and I cut this thing like this, dunk, 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 dunk. Okay, and I looked at that slice basically from this angle, then what I will see is that will be a DFT, will be X, okay, and it's a sampled sinusoid, it's a windowed sinusoid, so what I will see is basically clunk, clunk, side lobe, side lobe, side lobe, clunk, clunk, side lobe, side lobe, side lobe. Okay, this is that window, just viewed from this side. If I could have just plot this thing and played a little video over time, and what you would then have seen is basically this thing moving this way as the sinusoid goes faster, and then back as the sinusoid goes slower. And really that's the little time lapse you see here. We start slow, we go faster, we go slower, we go faster, and so on. Now this thing is actually difficult to visualize or to print out on pieces of paper. So what they normally do is they plot these color maps. And what you can think of is the color map really views this thing here from the top. Okay? So this picture here is viewed from the top. And what you do is you make high points, you make them light, like these, and low points, like zeros or something, you make dark. Okay, so this is like those points here. Okay, or the points here will be dark and the points there will be light on those little picture. And then you view it from the top. This thing is called the spectrogram. And then if you look at it from the top like it is here, then I can ask you, what is the instantaneous frequency of this sinusoid that's going wee, 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 wee? And I can ask you, what is its frequency at 600 milliseconds? And then you can tell me the instantaneous frequency. Happy with that? I'm going to do a few examples now where we actually see not just for a frequency modulated sinusoid like this, but for other signals as well, how we can calculate the STFT and visualize it with the spectrogram and what we can see from it. So the first example here is actually the one that we've been looking at in the lecture slides, frequency modulated sinusoid. It sounds like this. Okay. And so here what I do is I define the frame length. I say I'm going to keep 256 samples. I'm going to use a hop or a frame skip of 32 samples. So every 32 samples, I'm going to grab a window of 256 samples. You guys with me? Okay, and then I use SciPy's STFT function. I'm being fancy. I'm using a Hamming window for each of the DFTs. I'm using a Hamming window. Actually, where do I specify the window? It doesn't look like I'm specifying it. So, okay, that's a mistake. Okay, I run the STFT and then I plot the spectrogram, looking at this thing from the top. Okay, and that is what the spectrogram looks like. Okay, I'm only looking halfway to my sampling frequency, so I'm only plotting basically this bottom half here, but this is exactly what you get. So where I started with actually was this 2-chord example. Do you remember this? So I'm going to flip to 2 chords and then I'll flip back to sinusoid land. You remember this 2-chord thing? Okay, and I don't know where the chord changes from one to the other. I can't see it on the DFT. If I take the DFT of that, I don't know which chord is happening. Okay, so let's change this, and I'm going to do the 2-chord example. And you can see here I cheated beforehand. I prepped for the lecture, and so I figured out what the window length should be and where to look at in order to have a sensible plot. The 2-chord thing is sampled much faster than my siren sound, so I need a lot more samples. So I'm going to take a frame length of 188,192, which is really long, and I'm going to have a hop of 5112. Okay, so let's run that. And then I'm going to just plot the spectrogram, and I'm just going to stop it at 500 hertz, just so that we are looking at the kind of the bottom frequencies of my double chord. Okay, so let's just listen to it. Okay, and let's run this. Okay, and now this is the spectrogram that I get out. Okay, and so after how many seconds does the chord change? Just after 1 second, you can see that the chord changes there. That's pretty cool. And if you can look up on Wikipedia, you can actually tell me what the chord is at a specific point. Okay? So let's go back up here, and we just listen to chord 1. Just chord 1. Okay? Okay. So if I have one chord and I do the DFT and I get the spectrum, then I can see what frequencies are present in that chord. I lost that if I have both chords, but now I've got it back after taking the short-time Fourier transform. These peaks, if I scroll down, those are the same as these peaks in chord, this is chord 1 basically happening. And so I can see those peaks again. If I change my plot to go to chord 2, these will actually be the peaks of chord 2. So this picture here, you can think of it as kind of as a slice out of the spectrogram at that point. Okay, and I'm looking at that slice from the side. So that's pretty cool. You can actually read off. Like if I know what these notes are and Wikipedia tells me what a G chord or a C chord is composed of, I can tell you what chord is being played at that point and what is the second chord being played and when are these chords happening. Let me just go back to the siren. Here we have our siren again. And what I'm going to do now is I'm going to fiddle with the window length in order to show you that you want a long window, but you also want a short window. Let's make it short, okay, and see what effect happens when we have a short window, okay? So when we have a very short window on this slide, then the effect is that, remember the DFT, if I have n samples here, then the DFT will give me n samples here, okay? So if I have 32 samples, then I will have 32 little dots there that I'm grabbing. If I make my window 5, then I'm going to, in effect, have a sample of the spectrum at just 5 points. Okay, and so my resolution of my spectrum will get less. Let's shorten this window. It's 32 now. Let's make, it's 256 now. It's pretty long. Let's make it 64. Okay, and I'll run it again. You guys see what's happening. Let me make it 16. Okay, and so what's happening is there's actually just 16, it's half the DFT, so it's just 1, 2, 3, 4, 5, 6, 7, 8 points, okay, and then it repeats again. Okay, and so it's just the bottom half of the DFT that I'm taking. And the problem with the short window is, can you actually tell me what the frequency is at 0.4 seconds? It's actually pretty difficult to say what the frequency is, okay? And so by taking a very short window, very, very short window, the signal is stationary in that thing, but we're losing spectral resolution. Is everyone happy? Or, I mean, you need to be unhappy. This is not nice. This makes me unhappy, okay? Let me make the window nice and long. So let's just go back to 256. 256, here I can very precisely tell you what the frequency is at 0.4 seconds. I can read it off there, and I can maybe even zoom in even more. Okay, now let's make the window long. Let me make it 1024. Okay, so now we're taking a long window, which means actually my spectral resolution here, there's going to be like 1024 divided by 2 distinct points or bins on this axis. And so I'm getting a really nice resolution. But the signal isn't that stationary in that window anymore. And so we're starting to get this bleeding across time. Okay, let me make it really long. Let me make it 4096. Okay, and now you see this smearing over time because you're taking a very long window. Remember, this is our non-stationary signal. You're taking a window that stretches across basically multiple frequencies now. And so you get this kind of smearing effect. Is everyone unsatisfied? Okay, cool. I'm happy with your unsatisfaction. Let's just have a look at a few cool signals. Do you remember this DTFM thing? Someone pressing a button on a phone. 9123. And what we looked at in one of the previous videos was like I press one button and then I can tell you what button it is. Okay? But what if you're in a situation where you don't have just one button being pressed? Okay. Now, if I took the DFT of that whole signal, it would just be a blur and I won't be able to tell you what button is being pressed. But now what I can do is I can run the STFT, and now I get this picture. And what I can do is I can tell you how many buttons are pressed, whatever. Okay, and you can see exactly what, remember the DTFM is these two frequencies always going together. So this is my one frequency and that's my other frequency. Button change, this frequency, that frequency, and so on. Remember, when you press a button, there's two frequencies. And that tells you, the combo of those two frequencies tells you where you are on your keypad. So let's do, this is some speech. Okay, let's just listen to it first.
Dress, start. Dress, start.
Okay, and let's just look at this. Okay, so this is a little bit of speech. What sound is this? What's happening there? It's this from dress, start. Is the kind of highest frequency thing that we can produce with our vocal tracks. And so this is the s from dress. And this is the s from start. What's this? T. So t is a very interesting sound because it's called a plosive. It has a bit of silence when nothing happens, and then this little explosion. Dress. I actually close off my vocal track. Feel your tongue is pressing down that no air is coming out of my mouth. Dress. Nothing is coming out, right? Tart. Okay? And so this is the silence, and then this is the bit of explosion that happens. Okay? What are these two things? Vowels. Okay? Those are vowels. The e and the a, dress, start. Okay? I can, there's harmonics here, okay, of something. These harmonics, like this bottom line here, what's that? That is my pitch, okay? So if I was singing a perfect A note, okay, you know, it will be at the frequency of an A note, okay? And then there will be harmonics at whatever the multiples of the pitch is. So if this were a male speaker, that line would be lower, and then the harmonics would be tighter together. So you can actually, I think I have a male speaker here.
Where were you while we were away?
Okay, and you can see that the pitch, the lines at the bottom are more tightly packed. Okay, yeah, you can see some cool vowels happening there. Okay. So let's just listen to this and then see if you can pick up what's changing. So you can actually you can see where the bass comes in. The bass comes in here. Okay, just play it again. And if you were good, you could read off the note there that the bass is playing at that point in time. You can also see the breaks in the dum da dum. You can see where he basically stops the guitar. It's these little silences. That's the short time Fourier transform. Everyone happy?